All right, so today's topic is about complexity analysis using BigO notation. Now, that might sound like super complicated, but it's actually a simple concept. I'm not saying it's easy always to kind of identify it, but at its core, BigO notation sounds fancy, but it's really pretty simple to understand once we get into it. Now, I know some of you guys might be kind of up to the game already about knowing what BigO notation is, while others, you guys may have never heard of it or may have heard of it like, I have no idea what people are talking about. That's totally fine. Again, it's something that we should be able to kind of understand once we get through today. But kind of mastering it, kind of being really good at analyzing solutions, that takes more time. But let's get into complexity analysis. So you've maybe seen this slide before because I have shown you this slide. Again, the goals of a software developer are kind of twofold. I kind of just make it really, really simple here. One is solve a problem. So if you're given a project or an assignment or just like some requirements, you need to solve whatever needs to be done. Right? No matter how you solve it, you need to make sure it works. Because if you have something that's really efficient or really elegant, but it doesn't produce the correct results, well, it's not going to matter. Like no one's going to care that you wrote your entire program in like 3 lines of code if it doesn't give you the correct results. So always get to the correct results first. But once you do that, always be mindful that you can usually always make improvements. There's so many different improvements you can make. Again, structurally, we talked about this in the past, but like adding comments, some simple things like naming conventions. Also, like design patterns, you know how you structure your code, how you organize your code. Again, a lot of just like design-oriented things that can make an impact on how good your code is structurally. Also, again, using OOP when appropriate. That's another structural improvement you can make. Functionally, we've briefly talked about just kind of how your end user kind of uses your application. Do they have to click like 20 buttons to actually get to the result, or can they just click one button? Like I'd argue that one button is better than 20 different buttons that they need to click on. So there's like different features you offer for your application that's functionally making your solution better. But we're going to be touching upon algorithmically kind of how you identify improvements that you can make. So algorithmically, when we're talking about improving our solutions, usually falls into 2 main categories. One is execution speed optimizations. So again, just trying to improve how quickly your algorithm or application gets the correct results. The second is resource optimization. So usually this is focused on memory. So like how much memory does your algorithm use? This, I'll admit, is not usually a focal point for most developers because, again, memory is pretty cheap. Like if I need to double the memory of my computer, I could probably buy extra RAM to kind of handle that. But like doubling the speed of my processor, that's not as easily done, right? We're kind of hitting those upper limits of how fast our silicon processors can go. So doubling processor speed is not as easy. That's why creating algorithms that are really time efficient matter to us more than like memory and other resources that we might be using on our computer. So everything I'm going to talk about today is going to be related to kind of like speed optimizations, but the concepts still hold for for speed analysis, but same concepts hold true for memory analysis. I also want to take a quick moment to give a shout out to one of our students. So G-Don actually, I think, created a small lecture document on recursion and BigO analysis. So check that out. I think she posted it a couple days ago. So thank G-Don for taking the initiative there. Just another supplement resource here in case you want to know more about BigO analysis. But here, before you know how to improve your code, you got to know how to analyze and identify what can be improved. So again, the focus of this lecture is going to be how to kind of identify places in your application or your program that can be improved by knowing kind of how expensive a certain piece of code is. We're not going to talk too much about making improvements as in those optimizations or certain types of optimizations. That might be a future lecture, but that is not the focal point of today. We just want to identify what our code is doing and kind of how it compares time complexity wise. All right, so probably a question on your mind is, what exactly is BigO notation? Simply put, it's a way to represent the relative complexity of a given algorithm. Again, relative is a key word here. We are not actually measuring how long our algorithm takes. That's a different concern. We just want to know relatively how our algorithm is going to perform based on changing inputs. So if we change the size of our input, like let's say our inputs go from 10 elements to 20 elements, how is our algorithm going to react? Is it going to take twice as much, from the original to the new input size? Is it going to take twice as long? Is it going to take 4 times as much? Is it going to take 100 times more kind of like processing time to complete the algorithm. In terms of how you kind of pronounce the terminology, because we want to speak to speak, if you read a sentence that's formatted like this, the way you would read this or say this would be, this algorithm has O of n time complexity and O of 1 memory complexity. So you say O of and whatever the factor is. So O of n is a type of factor, O of 1 is a factor. We'll see a few more examples shortly. Any questions about kind of just introduction to BigO analysis or notation? So again, key takeaway here is we're kind of just talking about relative time complexity. It's just like a language. When we talk with programmers should know, like if I say something like, hey, this is O of n or linear time complexity, you should be able to kind of understand what they are talking about. One thing I want to mention again, BigO notation or analysis questions are pretty popular interview questions. So again, yes, you'll probably be fine after today if you never really want to deal with BigO notation to get through our curriculum, because we don't really ask you to kind of analyze solutions and kind of make improvements too often. But again, when you get into interviewing, definitely brush up on your BigO analysis, because like more times than not, you're probably gonna be asked to code up a solution and analyze your solution in terms of just talking about like, hey, this is my solution. It's O of n squared complexity because of these factors, and just talk more, again, speak to speak, talk to talk from programmer to programmer. All right, so there are different types of analysis you could do on a given algorithm. The most common is BigO notation, so that's what we're going to focus on today. BigO notation represents the worst case complexity. So if you think about your algorithm, assume the worst case in terms of the longest time it could possibly take to get to the final result. That is what BigO is concerned with. And that is what developers usually care about, because you don't want to care about best case, because that's not going to be your limiting factor. Usually you want to know, all right, given the worst like input in terms of what your algorithm is trying to achieve, if your algorithm is going to take the longest amount of time, you want to know how that's going to perform. So that's what BigO measures there. But there are a couple other things developers might kind of focus on. Big theta. This one's not too uncommon. This is average case. So again, we're not considering the worst of worst cases, but generally speaking, you get normal inputs. What's your normal runtime complexity? And that, again, that can be important for developers to know what the algorithm is doing. So you might have a terrible worst case complexity, but if your average case is pretty reasonable, you might be okay with your algorithm staying as is. And then finally, we have big omega. This is your best case complexity. I'll be honest, I've not really seen this ever really used, because we don't really care about best case. Like if you luck out and just get like the best input and you find your answer right away, sure, that's great. But again, best case is not really impactful in terms of knowing what your algorithm is actually doing or how it's performing. But again, that is an analysis that exists. Again, I'm sure it's used somewhere. I just have seen it. So again, BigO is what you're going to be commonly come across with. You might see big theta, again, average time complexity, but usually it's going to be BigO from my experience. All right, so again, worst case, which means if your algorithm happens to take the longest time, as in like your input for whatever reason, what you're trying to compute is just going to go through your entire array, for example, or you're going to do, again, just whatever every branch of your algorithm needs to be hit, that's going to be your worst case. Any questions about BigO, big theta, big omega? All right, we'll see BigO and big theta in a little bit more, but let's go forward. So again, we're going to talk about some common algorithmic complexities. Note that these are just a few. You can actually combine all these together. So notice we have n, we have log n. We actually have n log n as one combination. You can have a lot of combinations here. So just know that these aren't the only complexities, but these are pretty much the most common ones you can have. So the first one at the very top, O of 1, again, that's how you pronounce it, O of 1. This is known as constant time complexity. Then we have O log n, also known as logarithmic time. And going downwards, the lower you go here, the slower your algorithm is going to perform, relatively speaking, meaning as your input size grows, the slower and slower an exponential time algorithm is going to take versus a constant time algorithm. All right, so again, our goal is to be as fast as we can. So we want to target, make our algorithms if we create an algorithm that's constant time, that's great. That's pretty much the best you can do. If you get into like log n and n, these aren't too bad. once you start getting into like the upper limits here, like n squared, it's considered a bad algorithm. Exponential time, that's quite terrible. As in, as your inputs grow, your time is going to take longer and longer and longer. But let's actually kind of dive into these a little more in detail with some examples. So first one we're going to talk about is constant time complexity. Again, O of 1. These algorithms mean your execution speed does not change based on the size of the input. So again, if you're dealing with, let's go with an example of appending an item to a list. So I think it's probably more useful to see code than just seeing slides. So I do have an example here. Let's go to BigO. This is my example. So we have two lists. We have a quote unquote small list, which has 5 items in it. We have a large list that has 10 items in it. Obviously, this could be a way larger list, but kind of keeping it simple. I have a function here, and I want to analyze what is the time complexity for this function or for this operation. In this case, appending an item to a list is considered a constant time complexity, meaning if I'm appending into my small list, this operation doesn't care about my list size, meaning my small list has 5 items in it, and I want to append to it. It doesn't matter how many items there are. Append automatically knows to add to the very end, right? So I have 5 items. All append's going to do is say, all right, I know where the end of your list is, and I'm going to insert 77 into it, or whatever item you're trying to insert. So it knows, again, it does not have to go one by one saying, is this the end, is this the end, is this the end? Lists automatically know where their endpoint is. Append is going to say, all right, I know where your endpoint is. I'm going to insert at the very end. I don't care what's before this. Like if there's 5 items, if there's 5 million items, it does not matter for appending. So again, appending is considered an O of 1 operation, or also known as constant time complexity. So we have 10 elements. Again, inputs, this operation doesn't care about the size. So I guess I'll just copy exactly what I had before. Right. So again, it could be 5 items, 10 items. Append is a constant time of operation. Any questions about what we're kind of talking about here? All right. So hopefully you guys kind of understand that. Again, your input size in this case for this function here, the input size, which is my list, does not impact the operation here. It's always going to be constant time, the same amount of time, roughly speaking, for appending into a list that has 1 million items or 1 item, doesn't matter for append. So that's an example, a simple example of constant time operations. Let's move on to our next example, log n. So this is known as logarithmic time complexity. So execution speed grows logarithmically, also known as slowly, based on input size. So this is a common complexity for divide and conquer algorithms. You guys earlier had the fortune of coding up binary search earlier this week. Binary search is a log n operation. So hopefully you guys kind of remember the process there, where we have like an input size, we chop it in half, then we chop it in half again. We keep chopping in half until we find what we're looking for or realize that we don't have what we're looking for. So that's log n, because if you go from, let's say, 50 elements to 100 elements, you only get 1 more operation out of there. Even though you doubled your input size, your number of operations goes up by 1, because once you take your 100 elements and chop it down to 50 elements, well, you're back to your original problem, right? So your input size doubled, but your time did not double. It's going to just increase by a count of 1 or 1 extra operation there. All right, so again, binary search, we kind of saw that earlier this week, so I've not coded that up, but we will see it later on this morning. So keep that in mind. We'll help you understand binary search is a log n operation. Let's go with linear time complexity. So this is also a pretty common time complexity. We'll see. Execution speed grows linearly or proportionally based on your input size. So linear search algorithm, another algorithm you guys have coded up, is a good example of this. So this means, like, if my input size doubles, the amount of time my algorithm takes is going to likely double also. So again, we're talking about worst case scenarios. So if you want to see an example of BigO notation, or sorry, linear time complexity, also known as O of n time complexity, let's get another example here. So I think I have that down below. Hey, there you are. So I'm going to comment out my constant time one and use my new function here. So I created a function called find item greater exists. Basically, I'm passing in a list I'm passing in a value, and I want to find if any single value in my list is greater than the value that I've specified for this function. So here, I have a for loop that basically goes through each item in my list one by one, and then checks if that item is greater than my kind of target value. If it is, great, I return true. But if I don't find anything that's greater, I need to return false. All right, so again, let's talk about big O analysis. Why is this O of n? Well, because if my list contains 5 elements or 5 items, the worst case for this is that it's going to go through my entire list and not find what I'm looking for. So it's going to be, up to 5 iterations for this input, right? Because my small list has 5 items in it. I guess I added a 6th, but it's going to be up to 5 iterations because my list is going to have 5 items. It might need to go through the whole list and might not find what it's looking for. But then when my input size gets to 10, so my large list has 10 items, this could be up to 10 iterations in worst case for this input. Sorry for my typos. But yeah, let's take a look at this. So our large list has 6, 10, 9, 7, 1, whatever. It's going to go through my list. It's actually going to find a candidate that's larger. So in this case, it's going to get, maybe 3/4 of the way through my list and then find an item that's larger. So we're not always going to have 10 iterations. But if my list didn't have anything larger, like let's say I had, -1 here and -7 here. Well, now the worst case situation for an input here is that it's got to go through every single element, which is going to be 10 iterations, and not find what we're looking for and return false. So again, the average case might be a little better, but the average case is still a factor of n. So if we're talking about big theta, this still is big theta of n, because on average, this still has to go, probably some way through your list. Now it's not going to be necessarily as slow as going through an entire list in the worst case, but it's still O of n because you need to go through a certain number of elements here. The more elements you have, the more elements you probably need to go through. Again, average case, we don't focus on that too much, but understand that average case and worst case usually are the same, but not always. I'm going to pause here because I feel like I'm talking a lot. What questions do you guys have about linear time complexity? Cats.
I just wanted to ask actually about the binary search. Is it a different complexity if you, does it worsen the complexity if it's solved with recursion?
No, for binary search, if you do it recursively or if you do it iteratively, it is the same complexity. But that is a good question. The way you design your algorithms can matter for complexity. And we're actually going to see that in a second. So I'm glad you kind of brought that up. But yeah, for binary search, either way should be log of n. And we will see binary search shortly. But yeah, so linear, again, just means as your input grows, your relative time grows proportionally. Jake, did you have a question?
Oh yeah, I was just going to say with recursion though, like something like binary search, if you have massive amounts of input, then you'd have like space complexity issues with that, right? Like,
yes,
because you'd have stack overflow, your memory can only store so much.
Potentially, yeah. So Jake is right. When we do use recursion, so Kat asked about recursion. Yes, the time complexity may not change, but then there might be a new factor of memory utilization, right? So again, we're not usually too concerned about memory, but yeah, recursion does use more memory for its execution. So yes, there are memory constraints or memory analysis you do for recursive solutions. Yep, good point, Jake. All right, any other questions or comments about linear time complexity? And if there's any confusion here, please ask, because again, we want to make sure we're clear on what we're talking about, why this is O of n, because we need to go through potentially every single element. And we might have n elements, whether it be 5 elements, 10 elements, 1,000,000 elements. This algorithm right here might need to go through the entire list. So the worst case kind of grows proportionally as the input size grows. All right, I'm assuming we're good with that. Let's move on to another type. So let's go with log linear, also known as lin-arithmic time complexity. Kind of a mouthful to say. Execution speed grows log linearly, so it's n times log n is kind of like the factor here. I kind of say that's quickly. So execution speed grows quickly based on input size. One example of that is the merge sort algorithm. I bet most of you guys probably have not heard of this or not familiar with it. You go Google it, it's a popular sorting algorithm you might encounter. So we're not going to go over that here, but that's just one example of log linear time complexity for an algorithm. Let's move on to quadratic. This one we probably see more often. Execution speed grows quadratically, also known as very quickly, based on your input size. So the example I'm going to go with is finding a duplicate value inside of a list. All right, so actually, that's not what I wanted. Let me change that. Sorry. I want to find maybe a double value. I think I changed that up recently. All right, so we want to find if a value has a double value in there. So let's go back to our code. I think I have that coded up also. Let me comment that out. But again, the example I had written would work just fine. I'm going to get rid of some of these commented ones. Let's get our quadratic down here. Okay, so this is an example of quadratic time complexity. So here I have a function called find double exists, where we take an input list and we want to find if a double exists. So basically multiply one candidate by 2 and see if that value exists in our list also. So if we are going through our small list, for example, in this case, the way this is coded up, we're going to go through our list initially. So we're going to start with our 4 and then go through our list again. So starting with 4 again, and then seeing 9, 5, 12, and 2, investigating if we double the x value, if that becomes our y value. So we take 4, we double it here, so 8. We want to see if any of these values is equal to 8 for that first pass in the outer loop. For the second pass, we start with 9, and then we again start with 4 and go through it. So again, this isn't the most optimized solution, but that shouldn't matter in this case. So we'd start with 9 and say, all right, 9 times 2 is 18. Do we find an 18 in any of these items here? So it's going to keep going through that. Eventually, we're going to get to the very end, get to the 2. We realize 2 times 2 is 4. Then we start searching our list. We start here and like, yep, 4 is double that value. So we return true in that case. All right, so that's what my function is attempting to do, just finding any other value that's double of another value that exists in my list. So this would be a quadratic time complexity because we need to go through our list twice here. We have nested for loops. Oftentimes, this is a giveaway for n-squared complexity. If you have nested for loops over the same data, this means I'm going over my list one time, but for every single loop, every x loop, I'm going through my list again. So the outer loop adds a factor of n, and my inner loop adds another additional factor of n, but that's nested. So I actually get n times n, which results in n squared, and that is our complexity for this algorithm. So again, you're just counting up the worst case. How many times might this need to kind of iterate? So we look for a small list. This would, worst case, we need to do 25 iterations, right? We have 5 elements, and our inner loop might search all 5 of those elements again. So we can go through this 5 times. Every inner loop is going to execute 5 times potentially. So that's 5 times 5, which gives us that 25. So again, we don't really care about the exact number. We're just seeing relative performance. So if we had 10 items, I think I have 10 items here. Actually, I have 9. Sorry for lying to you. We should have 10 elements here. It doesn't really matter. But in this case, we have 10. Worst case, we need to do 100 iterations, right? Because 10 times 10 elements. So again, we don't care about the exact number per se, but we care about the kind of the difference between this and this. So we doubled our input size, right? We went from 5 items to 10 items. Well, how will our worst case get affected? Well, we went from 25 to 100. So our worst case did not only double, it actually quadrupled in this case as we doubled our input size. So that is showing us that this is actually, an n squared complexity because we are not growing proportionally, we're growing quadratically based on our input size. Any questions about this algorithm and why this is considered O of n squared, also known as quadratic time complexity?
I have a quick question.
Go for it, Jesse.
I just want to make sure I'm understanding when it says speed grows quadratically, where it just means that it's slowing down.
Sorry,
Correct?
yeah, sorry. I don't know if I've been
Okay.
misstating it, but yes, hopefully, yes, execution speed grows. So the amount of time it takes grows is what we're referring to. Yeah, so not the speed, but the amount of time it takes. So sorry,
Okay.
I should probably replace, yeah. Sorry, thank you for correcting me on that. Not the speed doesn't get faster, the time gets slower. So I should probably execution time should be written here. I'm actually gonna make that change right now so I don't forget it later. Thank you, Jesse. Yeah, want to make sure we are being accurate. So the speed doesn't get faster, the time just gets larger. Make that change. Any other questions while I correct my slides here? Shooting time grows, not the speed.
I have a question. So is it that anytime there's two loops that it's going to be n squared complexity?
Not always. So that is good. So again, seeing nested loops should send out like a light bulb saying, hey, this might be n squared, but it's not always. And we'll see an example where that might not be always true. But great question to have. So nested loop doesn't always mean n squared. It matters what data you're looping over. All right, let's get back to our slides here. Now that they actually say time instead of speed. The last one I'm going to talk about is exponential time complexity. This is considered a very bad algorithm in terms of the time it takes, because as your input size grows, your time is going to get much, 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 much longer. So I say this is insanely quickly based on input size. Your execution time grows. One example of this is the recursive Fibonacci algorithm. Key item here is recursive. So I know Kat asked a question about, well, if you did, binary search recursively or non, would that impact the time complexity? For binary search, it would not, but for Fibonacci, it would. So let's actually see this because we've actually dealt with the Fibonacci algorithm both recursively and non-recursively. Let's see how the recursive algorithm performs. So I'm going to comment out more code. Let's say goodbye to our quadratic friend, and then I have my Fibonacci friend here. So let's let's grab this whole bucket of code. Put some space here. I don't need my list anymore either. They can get commented away. All right, just making some space here. Let's drop in Fibonacci, and we want to uncomment that. All right, so we're going to focus on Fibonacci recursive. All right, so I've coded that up here. Again, hopefully this looks familiar because we solved Fibonacci recursively not too long ago. Here, I have a Fibonacci recursive function that takes an n value. That's the index we're going to compute. I have a global variable called calls, which I just want to use to track how many function calls I make into Fibonacci recursive. And then I have my base case here. So remember, every recursive algorithm should have a base case. So base case. And then you also have a recursive case. So if I have n equals 0 or n equals 1, by definition, Fibonacci of 0 is 0. Fibonacci of 1 is 1. Those are kind of hard coded or given values. Every other values depend on the first two values. So Fibonacci value of 2 is 1 still because you add 0 and 1 and you get 1. So that's what the recursive case is. Anything larger than n value larger than 1, we're going to have to recurse to get to the correct answer. So hopefully, again, you guys understand the recursion going on here. I have two inputs here. I have Fibonacci index 6 and then Fibonacci of index 12. Let's see how many calls are made for each of these operations. All right, so let's start with 6. We'll bring up my terminal. So again, this is an example of exponential time. So let's see that here. Clear. Let's go Python, BigO. All right, so fib index 6. The value is 8. Let's make sure that's correct. So we have 0, 1, 2, 3, 4, 5, 6. Yep, the sixth item or value at index 6 is 8. So that's the correct value. We made 25 calls just to compute index 6. Again, this is because recursion is kind of doing some duplicate work. Like to compute fib 5, we need to compute fib 4 and fib 3. For to compute fib 4, we need to compute fib 3 and fib 2. You guys kind of understand the duplication that's going on there. So what if we actually change this to 12? Let's add in into 12. So effectively, our input size is doubling, as in we're going from 6 to 12. How is our number of calls going to be impacted here? So if I run that, notice we went from 25 calls to 490 calls with this algorithm. Now, again, obviously this algorithm is not the best. There can be improvements made, but the way it's coded right now, we are kind of exploding in terms of number of calls we can make here. Let's actually try 18. I think 18 should be computable, but at some point, like once you get into the 30s, I believe Fibonacci just takes a long, long time. Let's try with 18 and see how this gets impacted. So I'm going to clear my terminal. All right, so notice what's going on here. We're just kind of exploding in number of calls. We went from 25 to 490. We grew by we didn't even double 12, right? We grew by another 6. We're in the close to 9,000 calls here. Let's actually double 12 and see what that looks like. And that's probably going to be the last one I do, because again, this takes longer and longer amount of time the higher I get. So 24, let's see how long that takes, or relatively speaking. All right, that had a slight pause there. I don't know if you guys noticed it, but we're at like 160,000 calls just for Fib 24. So again, kind of see how these call numbers are growing. It's exponential, 25 to 490 to 8, close to 9,000 to close to 160,000. Let's try 30 just for fun. I'm not sure how long it's going to take, but I think around 30 gets to the point where I don't want to sit here and wait for it. So clear. All right, it took a pause there. I guess it wasn't as long as I thought, but again, we're at 2.8 million now, number of calls we're making. So I think you guys understand that this is not a good algorithm, because we're making a ridiculous amount of calls for not that large of an input in this case. But the recursive Fibonacci algorithm is one example of having an exponential time complexity. I keep going to the wrong side. So that's one example. You're not going to see this very often. If you catch yourself coding up exponential time complex algorithms, probably want to reconsider it, try to find out if you can refactor it, or at the very worst case, if you need to still stick with it, try to find as many optimizations as you can to kind of improve the average time complexity. Or not the average time complexity, but kind of how your algorithm performs on average. Was there a question there?
Yeah, I had a question about the Fibonacci one. So it seems like a lot of the recursive ones, if you program them like suboptimally, like it'll have this exponential thing. And I'm wondering, like, since like the issue with this is like you're kind of recalculating like the same thing over and over like a million times, like, is it possible to just have like, maybe for this case, but maybe other recursive ones too, just have it like check a dictionary of answers before that it recalculated?
Bingo. Yep. Andrew's hit it on the nose. Yeah. So the problem with this algorithm as coded is that we're doing a lot of duplication. So yes, that is one common optimization for this structure, where you kind of cache answers in there. So if I've already computed like fib of 37 or fib of 17, I don't need to recompute that, because that's going to go down the line of 17, 16, etc. to compute fib 17. If I've done it once, I don't have to redo it. So yeah, storing in a dictionary and say, all right, fib 17, we've done that before, just give me the value instead of recomputing that. So yes, that's a very popular way to increase the complexity of certain algorithms where you're computing a lot of values repeatedly.
Would it change that to just not linear time, but the one afterwards where each input just adds the same time then?
That's a good question. I'm not sure how. So I think the official term for what you're describing is called memotization. I have trouble pronouncing it. Where's my? There it is. So what is it? Memotization, I think, is the buzzword.
There's memoization and
yes,
tabulation.
Yes,
as far as I know.
So Fibonacci, it's probably been done. So we could do Fibonacci. Thank you, Andrew. Recursive Fibonacci, yeah. So there's a Stack Overflow. You guys can kind of read this, and maybe they have a good answer here. I've not really looked into this, but yes, the idea is using a dictionary. So Andrew, you are correct. That would improve your, at least your kind of like average runtime, if not your worst case. Okay, so again, exponential time, very, very bad. You usually won't encounter this too often. Okay, any questions about our time complexities here? Okay, so we have this nice chart. I think this is kind of cool to look at. So this is a relative comparison of some of the time complexities that we talked about. So they're kind of shaded into different regions. I actually took this from bigocheatsheet.com. So let's take a look at that site, because it's actually a really cool site, in my opinion. So if I find my browser, let's go to BigO Sheets. All right, so again, this is kind of like a nice kind of summary site that kind of gives you a good background in BigO analysis and complexities. But this chart's pretty cool. So they kind of map out what you see on a chart, but notice that this is not equal scales on the left or on the y-axis and the x-axis, because the linear one, O of n, does not slice like diagonally through it, like a 45-degree angle. It's pretty flat here because they're trying to highlight the kind of the more complex or the more kind of the faster growing ones. So here, anything in the green region is considered very good. So O of 1 is just going to be a flat line. That is an excellent algorithm. O of log n is also considered good. Anything that's O of n, so linear time complexity, as your input size doubles, your time's likely going to double. That's still decent. That's still in the fair range, so this yellow shaded region. But then anything after O of n starts to get not so desirable. So O n log n is considered a bad algorithm. And then you get into the horrible range. So anything that's n squared or beyond, that's considered horrible in terms of performance. However, sometimes there's no way around it, right? There's no magic all the time, like magic in terms of optimizations or refactoring, where you can get away from n squared solutions. Sometimes you have to do n squared to achieve your solution, right? Because again, goal one is achieve the correct results. So sometimes you're stuck with n squared. That's fine. Just know that that's not going to be a good performing algorithm. That's where you want to then go into exploring, all right, I'm stuck with n squared. However, what improvements can I make? So one example, if we go back to something I had before, if I can bring back an old friend, let's go to our quadratic solution here. And again, we're not going to talk too much about optimizations. That's going to be maybe another lecture at another time. We'll just look at this algorithm and kind of notice something, right? So I can't get away from n squared. This is going to be n squared if I leave it as is. But notice here, one improvement I kind of thought of is, well, we're doubling x and trying to find the y values. Basically, we start at 4 here, and then we want to find anything that's equal to 2 because we're doubling the x. Well, what if we go the other way around? Like, what if we start at 4 and also look for both 2 and 8, right? Because 2 is going to be a value that doubles into 4, and then 8 is going to be a value that 4 doubles into. So we could do maybe an OR statement here to say, well, what if you do x equals y times 2? Now we're kind of doing 2 comparisons. That's not going to add much to our complexity because these are constant time operations. But now we're kind of being a little smarter. So we're looking both for a value that's double this value and a value that doubles into this value. So that's going to cut down some of our operations potentially. Our worst case is the same, right? If a double does not exist in our input list, our worst case does not change. We got to go through the entire list kind of quadratically or nested loops. But this will kind of have us find the answer if one exists a little quicker, right? So if I look at this list, if I had an 8 right here, well, this would start searching here and find this 8 kind of right away, kind of early on in the process. And that's going to save me kind of having to go to this 2 to find it. Actually, sorry, that's a bad example. The change I made here, when I start with my 4, this 2 will be valid because I added this case here. So we don't need to go to 4 to 9 to 5 to 12 to 2 in order to determine that 4 is a double. We're kind of checking both sides of, this candidate is a double or if a double of it exists by doing 2 different checks right here. Joseph, you have a question?
Yeah, I'm not quite understanding why that method would be faster. Even though both of those are constant, it's still the same amount of work. We're just making it do it at once. So how is that faster?
So yeah, let's be clear on this. So our time complexity has not changed. We are still O of n squared, as in this is still a quadratic time complexity because our worst case scenario is still going to be impacted quadratically, right? So if we double, if we go from 5 elements to 10 elements, our worst case has remained unchanged because a double might not exist. The reason this is, kind of an optimization is because, for example, with our small list right here, right? Let's say I did not have this piece of code here. I'm going to remove it temporarily. If I only had this, what this is saying is, we start with a value of 4. So we have x is equal to 4 the first time. And then our inner loop is going to start with y equals to 4, and then 9, and then 5, and then 12. Type 5, 12, and 2. So our inner loop is going to go check, hey, is 8 equal to 4? Nope. Then we got to continue and then say, hey, is 8, because x is 4 still, is 8 equal to 9? Nope. Is it equal to 5? Nope, nope, nope. So we go through our entire list here and we didn't find our answer. So we go back to our outer loop and then our next value is going to be 9. And we do the same operation. Is 18, because 9 times 2, equal to any of these values? We get nope. So we got to continue on. Once we get to our final value of 2 right here, we are able to say, all right, we have 2. 2 times 2 is 4. Do any of these values equal 4? And the answer is yes. Actually, our first value happens to equal 4. So in this case, we had to do some extra work. But now when we added in this part right here, where we said, well, what if we just search the other case also, where x doubles into something else? Now we catch our answer earlier. We're able to say, all right, we start with x equals 4. Well, is 8, do we find 8 anywhere in this list? The answer is no. However, this adds, well, can we double any value of y? So we double all these values. And then in this case, we have 2. So 2 times 2 is equal to 4. So we find our answer quicker, basically. We cut down the number of potential operations if we find an answer. So again, our worst case is the same, but our average time, or like, normal cases for like a random sample of inputs, we're going to find our answer quicker. So our algorithm is going to be quicker, but the time complexity has not changed. Again, those are two different kind of concepts there. So again, this is the idea of adding optimizations. Find different ways to improve your overall execution time so that you can potentially find your answer quicker. Any questions about that concept? So again, we're not going to talk too much about making optimizations or finding different types of optimizations. That's something I am interested in. Might try to do a lecture towards the end of the cohort about that. But again, our goal here today is kind of just to analyze our algorithms here. So again, this is still n squared, but we added a slight improvement here. Okay, so that's, again, a simple example of finding an improvement and kind of improving our algorithm. Let's go back to Fibonacci. So we had our Fibonacci here. Let's get rid of some calls. Fibonacci recursives, as we kind of talked about, not the greatest in terms of time performance. I mean, it is pretty elegant, it's pretty easy to kind of code up. Probably took me like minutes to do that. But what if we actually went to the iterative solution? Right? So if I can get both of these on the same screen, that would be ideal. All right, so we have our both candidates here. We have recursive. Now we have our linear solution here. So our linear solution is actually O of n. We have a range that we create. So we have an input value of n. We do a single for loop to kind of compute our values going upward. And then we return once we find our value. So again, this is a single for loop based on the value of n. So this is just adding a factor of n. Right? So if we're looking for Fibonacci 30, we're going to do 30 iterations there. If we're looking for Fibonacci 40, that'd be 40 iterations. So our complexity is kind of growing proportionally based on the input size here. Versus this was exponential. We're able to refactor it as in completely redo our algorithm in a different way, and we improved our time complexity. So again, this is possible sometimes, not always. Again, sometimes you're stuck with the complexity just based on inherently what you need to do. But other times you can kind of reimagine or kind of re-attack the problem in a different way, and you might be able to achieve a better time complexity. Any questions on those concepts? Again, making improvements, optimizations, that's one way to kind of just improve your algorithm, even if your time complexity does not improve. Other times you can refactor, re-engineer your entire algorithm. We get the correct result still, but we are a much better time complexity, in this case, O of n, which is much faster, relatively speaking, than O of 2n or exponential time. Stuff making sense here? Yeah, I got a thumbs up from Edgar, so I'll take that as positive. All right, let's cover one more thing and we'll take a quick break. So again, how do we analyze solutions? Again, it's not always obvious, but let's talk about, I had an example down here. There you are. So the way time complexity works is you only kind of multiply them if there are nested loops. So in this case, you might say, all right, well, I have 2 for loops. This is n squared. Well, that is not true. So again, these are non-nested loops. So this loop is going to take a factor of n, right? So this is a factor of n because we are looping through our list one time. Then we have a second loop that's also a factor of n. So again, we have 2 for loops. So yes, we are doing more work than a single for loop. Like if I had a separate function that was just this, sure, this is going to be slower all the time, but we don't care about the actual time it takes. We care about the relative performance in terms of the input size, right? So, we have 2 for loops. This is effectively O of n plus O of n. So we have 2 different for loops. So we're adding, 2 O of n operations together. That gives us O of 2n, but that's not actually a real thing. That actually boils down back down to O of n. What I mean by that is that this 2 is just a constant, right? The biggest factor here is n, right? As our input size grows, n is going to matter. This 2 is not going to matter as much. The same holds for like if we had an operation, let's say I had a nested for loop here, like for z in my list, and then I want to do something with like z plus or y plus z. This now is an n squared operation, right? Because we have a nested for loop. Let me say this is another factor of n, but since these are nested, this actually is n squared. This entire operation right here is n squared. So in this case, we have an O of n operation and also an O of n squared operation. So in this case, we get some formula like O of n plus n squared. So again, you're not going to see notation like this. This doesn't make much sense. This is actually just n squared complexity because it's the biggest factor here, right? So n does factor in. That's going to slow down our execution speed. But we don't care about the execution speed. We care about the relative performance. Meaning, if we double our list size, this is going to have a greater impact than this factor, right? So we double it. This is going to hold a lot more weight. That's why we say this is an O of n squared algorithm, because this is kind of like the time sink, or this is our limiting factor for how much time we take. Again, this does matter in terms of overall time performance, but relative time performance, only the largest factor matters here. Right? So again, that's kind of how you do the math here with multiple things here. Because usually we don't have simple functions. We have maybe 20 different for loops, and like we have other things going on. You just want to pick out the largest kind of time sink, and that is going to be your time complexity for that given algorithm or for that function. Questions about that? Okay, I think it takes a while to digest. So I think with that, let's probably take a break here. All right, so again, we've seen some examples of different complexities. Again, there's good, relatively speaking, good complexities that you might deal with, some not so great, and then some horrible ones. Again, not always possible to get away from them, but one we did not talk about was O of n factorial, which is even worse. Notice like how steep it goes, straight to the heavens, faster than O of the exponential time complexity. So I've actually not seen or come across one that's n factorial. I'm sure you Google it and say, hey, what are some common n factorial complex algorithms? But usually you won't see that. Exponential, again, that's pretty rare too. N squared, again, that is more common. We see nested for loops often. So that's definitely something we might encounter. All right, let's actually get to some examples and have you guys do some analysis. So we want to do some analysis examples. All right, so I've coded up a few maybe simple, not so simple examples. I'm going to ask some members in the audience to try to analyze the complexity for the given algorithms. Let's see how we do here. All right, so first student I'll call on would be Shun. Shun, could you maybe help me out and tell me what you think the algorithmic complexity, strictly talking about time complexity right now, is for this algorithm and why you think it's that?
Let me see. I think it's n squared because it's a nested for loop going through the same list. That's what I think.
Okay, Shun has analyzed this and said he believes it's O of n squared, so also known as quadratic time complexity. Answer the question is he correct? What do you guys think? Do you guys think it's n squared, or do you think there's additional or fewer time complexity factors here? All right.
I think it's n squared.
What was that, Brian?
So I agree.
Yep. All right, cool. Brian agrees. I also agree. This is correct. So correct, n squared complexity, because as Shun correctly identified, we have an input, which is some list. We are iterating through that list in an outer for loop, and also additionally inside our inside that loop. So we have two nested loops here. I added some extra kind of like filler here, like if statements. These don't add complexity. This is a constant operation. In terms of value greater than 20, that's again for your computer, that's a constant time operation. It's not going to have to like do this recursively or like do a for loop here. This is a one and done operation, so that's not adding anything to our time complexity. This is a constant operation. This is also a constant operation. We are taking x squared here, I guess. That's a computation for a computer. It's not going to be adding anything substantial for our time complexity here. Yeah, so the if statements kind of get ignored. Calculations here get ignored. So we are down to n squared, just two nested for loops over the same data. That is our worst case. So n squared is correct. All right, great job, Sean. Let's go to our second example here. For our second example, I'm going to ask, let's go with Porphy. Porphy, could you help me out here and try to analyze this and tell me what the time complexity is? Do we have Porphy with us?
Yeah, sorry,
no
I
problem.
was muted. So it looks like we're just going through the list one time and then checking for an argument on it. So I would say it would just be O and then N, right?
Okay, so Porphy has analyzed this and said we have a for loop. This is O of N. What do you guys think? Do you guys think O of N is correct? Do we have anything else going on here?
Does the counter count as a log?
As a log. So good question. So I believe this is actually going to be O of N squared. And now it's not obvious why this is O of N squared, but this is one lesson we want to take away here. So Porphy is correct. We have a for loop here going through our list. So this is a factor of N that we add, but we don't have another for loop here, but we do have a function call here. So again, the important takeaway here is if you are using any functions, you should also understand their time complexity, and that's going to factor in here. So this is also a factor of N. Basically, the count method, if I understand it correctly, like we could Google it, but the count method, it's not like some magic function that just knows how many instances or items you have of each type. It's going to need to go through every element and say, all right, I'm going to tally this up, keep track of it somehow. Whatever it's doing behind the scenes, it needs to go through every single element in your list. There's no magic way for it to say, all right, I could just kind of scan, 2 items in the list and know every count that exists. Does that make sense? Right. So if we want to implement this ourselves, we could, but we're using a built-in function for our list. We're using the count method. But again, if we want to do this ourselves, we do something like for y in my list, if y equals x, then our counter should go up. Counter plus equals 1. Right, so this line of code is basically doing something like this behind the scenes. Oh, this is item. Should have my naming, and I need a counter defined here. All right, so this is effectively what the count method is doing. It's some sort of for loop. Again, might be a little different behind the scenes, but it still needs to go through every single item in order to tell me what the count is for that given item. Right, so again, the important takeaway here is that if we're using additional built-in methods, those can add time complexity. So it is important to know exactly what that method is doing. Now, sometimes you may not know because this is abstracted away from me. I don't know exactly how it's counting it, but I can use an educated guess and say, well, we're going to need to investigate every single item in here. So it's likely going to be O then. And we can in fact try to Google this. I'm not sure if we'll get what result we get, but like, what is the time complexity for the count method in Python? That no typos, and count list method. Let's see if there's an answer here. All right, cool. So if you go to, again, any reference you're using online, always take a grain of salt. Like it's usually reliable. No one's going to write fake information, but sometimes it might be just amateur coder trying to write their blog. But based on the site, you're gonna kind of scan it. I think I saw Oven listed somewhere. Yeah. No, I don't want it. Find Oven. O of n. All right, there we go. So there you go. So this person has mentioned runtime complexity is O of n. Again, this isn't an official site, so that is something to take with a grain of salt. We could search other, Stack Overflow usually has good answers. So what is time complexity of count function? So again, you can actually look at the code. So it looks like this person dug up the code. Notice we do have a for loop here. So it is O of n. So again, sometimes you may not know. I'm not saying you should automatically know what every method time complexity is, but the important takeaway here is you should be mindful of, hey, if you're calling a function, whether it be your own function or a built-in function, you should understand that that might add to your time complexity. So in this case, again, it was kind of tricky. So again, no worries if that's kind of got you there, but we have a for loop here. And this effectively is another for loop. This count method is another for loop, so that's a factor of n. So this is also an n squared algorithm, even though it's not quite obvious right off the bat. So yeah, so a little trickiness there. All right, any questions on why this is n squared?
Just for example, say if we just did an append to the list, that would just still be O of n, right? Versus the count method.
So yes, append is actually constant time, so it's O of 1. But yeah, if we just did like my list, let's say, I don't know, we're going to append to it, but let's say append x plus or item plus 1. I don't know what we append. Yeah, this is a constant time operation. Again, a lot of computation. So we did like other stuff like y equals item times 7. I'm just throwing nonsense here. Again, computations are constant time. Appending is constant time. Yeah, so in this case, if we have a factor of n plus a factor of constant time, O of 1, that's just times O of n. That's just going to be O of n. I can actually type what I'm trying to talk about. Yep, this again, the biggest factor wins out. So in this case, the biggest factor is O of n. So this is still O of n. This O of n comes from this for loop, to be clear. Okay. All right, so that was n squared. I have one more example. So just kind of get familiar with how to identify code. Let's go with Philip, if you don't mind. Could you assist me here and try to tell me what you think the runtime complexity of this algorithm is? What is the time complexity?
Can you hear me?
Yes.
Yes. All right. Let's see.
And yeah, while Philip is kind of analyzing the code, hopefully everyone else is trying to look at this code again. Take some time to digest what's going on. So let's take a few seconds here. But yeah, Philip, whenever you're ready, no rush.
Probably say linear time. So we have one for loop that's going through the original list, creating a second list, and then that second for loop is going through that second list. So that'd be O to the 2n, which reduces down to O to the n, I think.
All right, so Philip has analyzed this and he has determined this is O of n. Does anyone else agree or disagree? Do we have a different time factor or any analysis that you guys have that might differ? Andrew Tran, you have your hand raised?
Yeah, I actually thought it was exponential time because so lines 93 to 96 create the first list. Worst case scenario creates the full one. Then you have to loop through the entire food list, which is the entire thing. Then you have to loop through again the original list and and since that's two nested for loops, I'm guessing it's exponential time.
Yeah, so good thought there. We do have nested for loops here, but again, this is where again we got to analyze exactly what's impacting our algorithm here. So Philip is actually correct. This is O of n, but it's not always obvious. So let's actually talk about why this is O of n. So good job, Philip. That's correct. So again, I added some extra stuff here, but our input here is my list, right? So the first thing we're doing is we defined a list here. This is not any additional complexity. This is a constant operation where we create a list. That's fine. But this is our first kind of like factor that adds in here. We are going through my list. We're checking if the item is a string, then we append it to our food list. So we're creating a new list. Basically, this is a factor of n because we are going through every item from our input, factor of n, also known as O of n. All right, so this operation is O of n. Keep in mind that this is not nested within this loop, so they are not going to multiply, they just add. So I think Andrew said something in there about we had O of n, or maybe Philip, I forget, and we're going to add some other factor. Whatever factor this adds, again, it might be O of n, might be something worse or less. And we're going to add those together and take the worst, kind of like the worst factor of that combination. Again, we're not multiplying this because these two are not nested. This for loop does not impact this for loop directly. All right, so then we get down to this for loop. And the question is, well, what's the complexity of the highlighted code right here? Well, we are going through our food list, and keep in mind that food list is proportional to my list. So for the most part, my list and food list are going to be the same size. Sure, maybe we don't append all the items, but you should assume that food list is going to be larger if my list is larger, right? Just kind of, that's just generally how the algorithm is going to work. Now it's true, like my list might have all integers in it, and then this is not going to append anything. Fine, that's like a special case. But if you can assume like this is going to have some strings, and like let's give a sample input, print example 3. You know, I would assume a sample input. Now I'm just making assumptions right now. But let's say a sample input is bagels, since we were talking about bagels earlier. And then we had maybe some digits, 55, donuts, I don't know, true. We could have any data types we want. We have another list here. Whatever. You guys get the idea. So let's have a muffin at 3 a.m. So our input, I'm assuming is going to look something like this, where we have some strings. We have some things that are not strings. Regardless, food list is going to be proportional in some respect to my input list right here. And this should be a list. Sorry. List. So food list adds a factor of n also, because it is proportional to my list. So that's O of n. Now we get down, well, we have another for loop here, and this is a nested for loop, right? So our rule of thumb before was, well, if we have a nested for loop, that's usually n squared, right? So it's tempting to say, well, this is another factor of n. Well, great, that's going to be n times n, meaning we have n squared. However, that is not what's going on here. And this is where we actually need to look at the code and determine what's going on here. Yummy list is this list right here. This list is not growing in any manner. Regardless of how large my list is, my list could have 5 items in it, could have 500 items in it. Yummy list is going to be constant here, right? It's just donut, cake, pie, and muffin. So this is a constant size. So this for loop is not going to change based on the input. This is always going to be 4 iterations at most. So this is actually a constant time operation in relation to my input, as in this does not change even if my input doubles or triples or quadruples. So this does not actually add a factor of n. This might, if you want, maybe a factor of m. Because this is still, you know, we're still doing a for loop. Like if we need to grow this, the value of m has some impact, but that m is not related to n. And again, this gets kind of alphabet-y, I understand, but we're concerned about how our input impacts this algorithm. So this might be considered an O of m operation, where m is just a different factor, but O of n plus O of m is going to be O of n. Sorry, m and n are really similar. Let me just go with a different letter. Let's go O of q, if that's kosher. So again, this is adding some additional time, but that is not related to my input. So like if we did something O of n plus O of q, for example, that's still going to be O of n, because n is the one that's going to be impacting us more. This q is kind of constant. You can maybe argue that this is actually a constant time operation. But this for loop does not add another factor. N is the important takeaway. So we have a for loop over our initial data, some other additional work we're doing, but not related to our input. So this block right here is O of n. So that's an O of n plus O of n, which is O of 2n, which we saw before, which boils down to O of n still. That might be a little confusing, so we want to make sure we take time for questions. Joseph, do you have a question about that?
I might be thinking a little ahead or completely off base, but if Yummy creates an O of Q and we're not using that in this current time complexity calculation, but we're still getting that, would the next step off of Q be like Q squared?
So I might need to get you to elaborate a little bit more, but I think that the question is about what time complexity is this particular for loop adding? Again, this value is not changing. Sure, this might have 1 million records in it. Let's just say this has 1 million in it. So let's just, again, use your imagination. I can't really simulate that right here, but let's say, imagine 1 million items here. Right, that's gonna be some cost, right? So this we're saying is Q. This is the factor of Q that we're adding in. So here, if you guys can bear with my comments all about, this is an O of Q operation, right? So if this has 1 million items in it, we're gonna do 1 million iterations here, which is a lot. So that's not negligible. However, that's still not growing with our input list. So let's say our input list is 5 items, and then it grows to 10 items. Well, sure, we're still doing 1 million iterations inside here, but our relative performance is not changing based on the Q factor. It's changing on my list. So early on, like when my list is very small, sure, this is gonna hold a lot of weight, but you think about all cases. So once like my list is like 1 billion records, well, sure, 1 billion records times like 1 million records, that billion is the heaviest weight. So your input is the one changing. Yummy list is not changing at all. So that does not impact your relative performance. Again, relative performance is the key here, not absolute performance. So again, yes, this will slow you down if you have 1 million records, but that is not what's impacting your algorithm as your input changes.
Right, I guess I'm trying to understand the growth of the branch. So once we've created O of Q, I guess the proper question would be, what's the next step beyond O of Q?
I'm not sure what you mean beyond over Q. So like, again, Q is just an arbitrary name I've given this. So like N is just an arbitrary factor that we use. So Q is just a factor that's part of our algorithm. So we're adding a factor of Q with this operation, but that does not impact our original input. So our input's dictating how long this is going to take, relatively speaking.
Okay.
I feel like I did not answer your question there fully. Apologize if I'm struggling to kind of understand fully, but we do have different things impacting your algorithm, but our food list / our my list is giving us that factor of N, so that this is an O of N operation.
No worries. I'll swing back around after doing some research. Maybe I can describe it better.
Okay, yeah, apologies for maybe not helping me out there, but so this is Philip, I believe. Philip, good job. Yep, this is O of N. Even though we have nested for loops, these for loops are independent in terms of yummy list is not impacted by our input here. Okay, more questions? Andrew, do you have another question?
Yes. A function with no input, could it be said that it has constant time?
So it, yes, I guess. So you're saying if I had like another example here, example, no inputs. How do I answer this? So if I do define example 4, Andrew's asking, well, what if we taken no inputs, but we had something like, you know, x equals 2 or x equals whatever. Then we did a for, say my list. Let's say we had something like this, x plus y. So now the question is this function constant time? And the answer is yes, because anytime we call this function, it's always going to be the same runtime, because my list is not changing. However, you know, this is a nested for loop, so you can argue if, you know, if this changes, then this part of your algorithm is actually n squared. So it depends what's changing in your application. If my list is never going to change, well, this is a constant time algorithm. So if I call, you know, example 4 here, I know exactly how much time, or like it's not going to, nothing else in my application impacts how long this is going to take. Like, yes, we are doing, you know, things repetitively here, but this is constant. But if this were ever changed, like if this is user input or might be random, then yes, you would say this is n squared complexity, because we're doing 2 nested for loops for something that might be changing. But if you compile this as is, well, we know this is constant. This is never going to change. So this, in effect, can be deemed constant. I mean, it's another factor. So if we had like another function, I think I'm getting maybe a little too into the weeds here. example 5, let's say this took in my list. And then this function called example 4. Again, example 4 is not impacted by this list that's coming in. So, if I did something with my list here for item in my list, let's call example 4 each time, just for fun, and then we print out item. So in this case, we have example 5, which is a function calling example 4. Again, the input's example 5. This adds O of 1 complexity, because the input here is not, example 4 doesn't care about it. So whatever it's doing here, yes, it's going to take up some time, but based on this input, this algorithm is O of n, because example 4 adds a factor of constant time. Does that kind of make sense? I know it's probably not the best explanation, but yeah, it matters on how your application changes, the inputs, the data that you're dealing with, how that impacts your algorithm. So if you have something that's constant, then fine, that operation is considered constant. Joseph, do you have a follow-up question there?
No, sorry, I forgot that was up.
No problem. All right, so let's actually get to one last thing here. So one thing that we kind of learned from example 2 is that methods that you call or functions that you call do matter. If you go back to our handy dandy cheat sheet here, again, this is a great site. So just seeing the chart, if you scroll down though, this is going to lead into our topic for tomorrow, which is data structures. Why do we have different data structures and why do we need to use them? Like, why can't we just use a list every time for everything we're doing? The answer is, well, sometimes you care about performance. So here, array is the same thing as list in Python, but you have average time complexity and also worst time complexity. And they also talk about space complexity, which we haven't focused on too much today. But notice, let's compare an array versus a single linked list. That's another data type or data structure that you might encounter. Notice for an array, accessing an item in an array is constant time, meaning if you need to constantly look up items in some data that you have, arrays are a great choice because accessing them, basically finding what you want, like reading a particular value out of an array, it's constant time. That's the way an array is designed, array or lists in this case for Python. However, if you need to search through a list or an array, that's going to be O of n, meaning you need to go through it kind of every element to find what you're looking for potentially. That is the worst case. You might need to do O of n to search for items in there. Again, access means, hey, I want the third item in my list. Great, that's constant time. Search is, hey, is the value of 77 in my list? Well, I don't know, let's go find it. That's gonna be worst case O of n. However, let's take a look at versus a single linked list. I guess we didn't go through all the operations. Inserting an item, that means in the middle of a list. That's gonna take O of n because every other item needs to be shifted over. So just to make sure we know what we're talking about here, we're not talking about appending. We're talking about, I have some list. Let's just get another file here. So if I have some list, let's say my list is equal to 4, 5, 8, whatever. If I want to insert something in the middle here, I believe that is, actually, I don't know. Let's go back to this. Insert item into list. Is it splice? That's Python. Cool, an insert method. So you want to insert the index and the value. Okay, cool. So if I want to insert something, I would use the insert method. So I want to insert the value of donuts at index 2. All right, so let's do this and print it out. Got donuts on the mind. Nothing too surprising here. We should not be surprised what blah.py prints out. Notice that donuts got inserted into where the second index should be. So this is actually an O of n operation because when we do that insert, all these guys had to shift over in memory. Again, this goes through our data structures talk tomorrow, so I'm not going to get too into that. But understand that these don't just kind of like say, all right, cool, we're automatically moved somewhere else. We need to go one by one and kind of shift them over in the array so that this is no longer at index 2. This 8 is at index 3 now. This is at index 4, index 5. That operation is O of n to kind of insert in the middle. So going back to our cheat sheet, that's why insertion into an array is O of n. If you're trying to insert into the middle, or if you're trying to delete from the middle or anywhere in the array, usually, it's going to be O of n. Versus if you look at a single linked list, notice that insertion and deletion are O of 1, meaning constant time. They're really, really efficient. So again, it comes down to your use case. Questions you'd ask, hey, am I retrieving items often? If the answer is yes, well, you might want to consider using an array like we've been doing before. Or if you're having some operation that needs to constantly add and delete items from the middle of your data structure, array might not be the right choice because linked lists are very efficient for deleting and inserting items. If you know how linked list works, you know how a linked list works, you probably can understand why that's O of 1. If you've never heard of a linked list, don't worry. I think Data Structure Tomorrow will cover it potentially, or you could Google it. But especially, it's just kind of like a chain of things. Like you can imagine maybe like paper clips attached to each other. If you need to insert something, you just kind of unattach two pieces, insert there, and that's kind of how a linked list works. All right, so again, many different data structures. I'll be honest, I don't know some of these. I don't know what a Cartesian tree is offhand. I don't know what a splay tree is. So some of these I've never heard of, but they are different time complexities. So keep that in mind when you are determining what data structure you use. Okay, also space complexity can matter. We also talk about sorting algorithms sometimes. So we have a lot of different sorting algorithms. Actually, there's a cool YouTube video. I wonder if I could find it. YouTube different sort methods. I might need time to find it. All right, I'm not gonna look at a 6-minute video. I'll try to find it later, maybe for stand down. But there's like a cool video that compares all these or a lot of different sort methods and how quickly they go through certain data to sort them. It's kind of cool to see how they operate. But again, these have time complexities also. So don't always just say, all right, I know one sort method, let's always use that. There's different things you want to factor in, as in, do you care about average case complexity? Do you care about worst case, best case? Different factors matter. Also space. Certain sort methods take no space, additional space. Bubble sort, I believe that's one of your challenges for this evening. That is a constant time operation in terms of space. You're not going to reserve any extra space for that. However, some other ones require additional space considerations. So again, this is just our kind of lead into our data structures talk tomorrow. Why do data structure matters? Well, time complexity factors into that. Any questions about data structures? Again, we'll cover more of that tomorrow, but just understand they matter. Okay, so definitely look at this website. So that's bigocheatsheet.com. I think it's kind of cool just to kind of get a visual of some of the things that are going on. But let's get to one more thing. So I think it's time for our main event. So maybe someone out there has been sitting there and saying, well, all right, we've covered linear search, we've covered binary search. What's the big deal? Why should I care about binary search when linear search is easier to implement and it gets the job done, right? Well, let's actually have an algorithmic face-off or algorithm face-off here. So we're going to pit linear search against binary search and see how they fare with different data sizes here. So I've actually coded all this up. Porfi, you have a question?
More of a comment. I believe it was Andrew Liu that he shared a really cool link that kind of had a bunch of algorithms lined up really, really pretty. It was a nice way to look at it. I don't know if you want to use that too.
Was that in the Zoom chat or the Quebec chat?
I think it was in the Slack. Let me double check though.
Okay, yeah, I guess you guys can look at it.
I posted it in Zoom chat. I can post it again.
Gotcha. Yeah, I'll check it out when I get a chance. But if you guys are curious, definitely take a look. There's a recommendation to check it out. All right, cool. So we're going to compare linear search versus binary search and just see how they fare. So again, these are two algorithms that you guys have coded up as your challenges in the past. Let's take a look at them. So if I go to my main events, let's go to our contenders here. So we have linear search over here, and then we have binary search. So both of these together. All right, so here are our contenders. All right, we'll put binary search on the left side. So let me get rid of my terminal. Let's make this condensed a little bit. All right, so these are our two contenders. In our left corner, we have binary search. So I've coded it up. There's no tricks here. You can just kind of accept that this is a working solution. I chose the iterative approach just to save on memory a little bit. But this, I actually created a class that takes in some data. And notice that we had to actually sort our data. So this is actually a downside of binary search. In order for binary search to work, there's some overhead in terms of we need to ensure that our data is sorted. We'll talk about that in a bit. But once we have our data, if we call our find method for some item, we should be able to find our item using the binary search algorithm. Now, in our right corner, we have our contender linear search. Now, I've also created a class for this. We take in data, copy it in, and then anytime we want to find something, we just do a for loop, look for an item. If we find it, great, return true, else return false. So let's kind of just take a look at both our contenders here and see what we're dealing with. So definitely our binary search is a heftier contender here, right? This is way more lines of code, right? This is probably like maybe 20 lines of code versus this is merely 4 lines of code. So in terms of just code bulkiness, I'd say linear search wins in that consideration. So sometimes how much code you're writing does matter, right? If you have to write 1 line of code versus 1,000 lines of code, that has some impact in design decisions you might make. However, time complexity is usually the biggest factor that we are focused on. So in this case, although this is more elegant and simpler to understand and implement, we are kind of achieving some better complexity. In this case, we have binary search, as we mentioned before, is log O of log n complexity, versus linear search is a linear time complexity algorithm. All right, so again, I've coded both these up. There's no tricks here. Just kind of assume that they work as intended. So we have our main events that I've coded up. If I can go back to my files. Sorry, before we get to that, any questions on binary search or linear search? Hopefully we can understand both algorithms. Okay, so I've kind of set up a timing situation here where I create my data structure, which can be even numbers only. I'm going to shuffle that data, so it's not going to be sorted. Keep that in mind. They're kind of starting off unsorted. I'm going to initialize a linear search instance and a binary search instance for my classes I created. And I'm going to run this a certain number of times. So my sample size is 10. So it's going to search for 10 random items in both of these lists. So both lists have the same exact data. I have a 10% chance that the data does not exist that we're looking for. So in this case, I'm just creating an odd number. And I know that all my inputs or my elements were even. So if I create an odd number, that's not going to exist. So 10% of the time, we're going to search for an odd number that does not exist in our data set. And then I'm timing it. So I'm using some timer libraries from Python. Basically, I just want to know how much time it takes. I'm aggregating the time for each contender and then averaging them out based on the sample size. So we should see, again, generally how they compare against each other. Don't worry too much about understanding what I'm doing here. Just kind of want to walk you through that we're creating some data based on how many elements we want. We shuffle up that data, and then we try to find some items using linear search and binary search. So let's get to our main event here. So if I go into my folder for main events, we're going to run main events.py. Right now we have 10 elements that our contenders are dealing with. So this is round 1, 10 elements, linear search versus binary search. So let's run main events.py. Let's see how they compare. So again, remember, we're looking for the quickest time. It's the smallest value we see here. So notice that linear search actually beat out binary search here. So linear search took like 0.00092 versus binary search was a magnitude larger here. So binary search actually lost this round here. And now you might be thinking, sitting there, all right, well, cool. So linear search is easier to implement, it's less code, and it's faster. So great, linear search is obviously the winner here. Well, not quite. This is just round 1. So if you think about a boxing match, it doesn't last 1 round. It usually lasts multiple rounds here. So we started with 10 elements. So for small sizes, the linear component, the linear factor doesn't really, matter too much because we just have a small input size. What if we change this to 100? So now our data range is going to be 100 items. Linear search and binary search are going to have to search have 100 elements that's going to deal with. So we go with 100. Let's see how our contenders fare here. All right, notice it's pretty close actually. If I ran this like probably 10 times, I bet linear search will win half the time, binary search will win half the time. It just comes down to like the data that's looking for. So let's try this a couple times. All right, ran that. All right, notice in the first time we ran this, linear search just won by a small margin. Notice the significant digits here. Second time, binary search won by a slim margin. Again, so they're kind of going back and forth here. So we have 100 elements. They're kind of neck and neck, I would say here. So I'd say round 2 is a tie. They're both pretty close in terms of how long they take to find items. Okay, cool. So first round, linear search won. Second round, let's call it a tie. Now let's go to 1,000 elements. I'm going to add 1,000 elements to our data set. Let's see how our contenders kind of are doing in round 3 here. All All right, notice we have kind of a switch in round 3. Binary search is still pretty slow, or sorry, pretty fast, as in we have a pretty low number here. We have 2 leading zeros, but now linear search is kind of creeping up in terms of how much time it takes. Notice we're at 0.03, so we're by a magnitude of 10. Linear search is slower. All right, this was 1,000 elements. Now, if you think about the real world, think about your Googles, your Amazons, your Apples, your Microsoft, like they are not dealing with 1,000 in terms of data in the thousands. They're probably dealing with data in the millions. Like Google probably has 1 billion search pages it's searching through. So 1,000 is not really significant for the real world. What if we jazz this up a bit? Let's go to 100,000. So linear search, 100,000 elements, and binary search, 100,000 elements. All right, so now you can kind of see where this is going. Linear search took 4 milliseconds on average, versus binary search is still kind of sub 1 millisecond. And this is only for 100,000. That's, again, that I would say that's still not sizable to the real world. Let's go to 1 million items, and you're going to see that these are just not, it's not going to be a contest anymore. Notice we're actually hanging here. So that took 78 milliseconds on average. Again, I'm doing 10 samples. So that you can kind of see that this is kind of getting out of hand in terms of no contests, right? Binary search is kicking linear search's butt as we grow larger. Let's try, I'm not even sure if 10 million is going to run. So let's just run this while I talk about it. So let's do its thing. It's going to take some amount of time because linear search is being very slow. But some things we want to talk about here. Why is binary search better in this case? Well, for my particular example, we are searching for multiple elements in the same data. Keep in mind that this benefits binary search because when we create a binary search, we had to sort it one time. This is actually adding a factor of n log n the first time here. So when we create our binary search class, this is some overhead. Sorting is not a free operation. So I'm guessing that the sort is going to be n log n, which is actually worse than linear time. So if you think about that, for small data sets, this is going to matter more because linear time is O of n versus the sort is going to be n log n. However, since we are finding multiple items, we only do this once. Each successive find does not have to resort the data. We sort once and we keep finding different items each time. So binary search benefits from that aspect of this challenge here. Notice we got our results back, and yeah, it's like a magnitude of what, 10,000, 100,000 difference. So as you might see, this is why binary search is a preferred searching algorithm. Yes, it takes more effort to implement, but usually the time complexity matters more than your effort as a developer. Not always, but usually that's going to be something that you care about, especially for large data sets. So that matters also. If you're writing an algorithm that's only going to deal with like tens of items, maybe hundreds of items, then your search might be fine. But if that's ever going to expand into like the thousands, millions, you probably should refactor it. Else you're going to suffer from some slow processing time. All right, so that was our main event. I think we could crown binary search the winner. So let's give it a title belt. Winner. All right, so that was our main event. Hopefully you guys kind of understand, again, you're getting the correct results with both of them, but binary search is a better algorithm because it has a better time complexity. Again, this is O of n, sorry, O of log n versus O of n. As we saw on our charts, so we have O of n, this is linear search, O log n is down here. It's kind of hard to see here. We had 2 hands raised, so let's go with Yilin.
So I just have a question out of curiosity. So in your second round, when you running the function based on the same amount of elements, like what's the reason the average time would still fluctuate like a little bit every time you run it?
So these timers aren't precise. So again, it's not going to be the same exact time every time. Again, these are pretty small numbers, so your computer's not always going to take like exactly 0.1 millisecond to do its operation. So that you're going to see some fluctuation. That's why I kind of created some samples. So instead of just doing 1 run, I do 10 runs each time to kind of average it out. But yeah, there's going to be some fluctuation. And I don't care precisely about the numbers. It's more about the relative comparison between linear and binary. So yeah, this is going to change and run this a couple times. I'm not going to run it for 10 million. Let's do it for 100,000. Yeah, it's going to be some variance. Again, it might be because my computer is busy doing something else at that time. I'm not sure what impacts these times, but again, they're close enough. It's 0.022, 0.23. Again, the magnitudes are what I care about more, but yeah. Also, the timers, as I mentioned, there's probably more precise timers. These are maybe not the most precise. But for my needs, they get the job done. Shun, you have a question?
Yeah, so binary search is time complexity of O log n, but
Correct.
it takes O of n log n to sort it. Is it because we assume that for binary search it's already sorted?
No, well, for binary search to work effectively, the data must be sorted. That is a prerequisite
Right.
for binary search to work. So in this
Okay.
case, I opted again. I didn't want to handicap any of our contenders. So for the main event, I actually shuffled our data. So this is going to be non-sorted. So binary search again has some overhead here. So again, this needs to sort, which adds overhead. So one thing I want to point out: binary search is better if we need to repeatedly search for elements. If we're only searching for one element ever in our data, you might want to consider a linear search if your data is not sorted, because sorting that data is going to add n log n factor, which is slower than O of n. So again, this particular example, we are repeatedly searching for a random item. So in this case, we do it 10 times. So again, binary search benefits from that because we sort once and then search 10 times. So that's just better for binary search. Because binary search at its core is log n, but that relies on a data being sorted, if that makes sense. So if I hand you sorted data, you should always be like, all right, I'm always going to use binary search. If I give you unsorted data, then you need to ask a question. Well, how often are we searching in our data set? If we're going to do it once, maybe just use linear search. If we're going to be searching for like multiple items in our data set, then maybe binary search would make more sense.
Thank you.
Yep, great question. Andrew, Trent?
So the case where you have the data sorted inside your binary search, where you have to sort it inside of the function, is we can say it has a worse it has a worse big O than like the linear search.
Yes.
But it's still faster in bigger cases.
In this case, yes, because we're repeatedly searching for something. So let's say, but yeah, if we had, the size of the input matters too. So if we had one sample, like the relative difference would be slightly different, but binary search would still win. Because we had to do an n log n operation on 100,000 elements, but again, the way log works is going from 100,000 to a million. Log is just like you're kind of doubling the work, not multiplying by a factor of a million or whatever, or 10 or whatever that factor was. Okay, so that was our main event. Let's wrap up our lecture. So key takeaways from today's lecture. So just at a high level, just know what BigO notation represents. Now, I'm not expecting you guys to be experts in analyzing code at this point, but again, if someone asks you, hey, this algorithm is big O of n squared, hopefully you can understand what they're talking about, and then you kind of pick out, all right, I see nested for loops, I understand that the input is impacting my algorithm in this manner. So again, BigO notation represents the relative time performance of your algorithm based on the input size changing. I said time there, but again, you can substitute pretty much everything I've said for time, you can substitute for memory. So again, memory is a factor sometimes. You can use BigO notation for memory as well. Also know how to analyze your code for algorithmic complexity. So this, we went through a few examples, kind of pick out, if you're doing a for loop over the data, that's going to be a factor of n. If you have nested for loops over that data, that's usually a factor of n squared. Understand also those, those traps you can fall into. Like not every nested for loop combination is n squared. You need to make sure that you're actually being impacted by your input data. Last thing I ask of you guys, again, we're still very new to development. We're still focused on, again, solving a problem, and that's basically our biggest problem right now. But once you kind of get more comfortable with solving problems, always be just mindful of writing efficient code. Maybe you aren't there yet. We're like, all right, I'm not sure how to refactor this, or I'm not sure how to add optimizations. That's fine. Just kind of understand as you're writing code, kind of have in mind like, okay, I'm adding another nested for loop. This is going to add a factor. I know that n squared solutions are generally considered bad. Just have that in your mind. And then, as we get better with writing algorithms, we'll get better with maybe applying optimizations or understanding how we could refactor our code to at least cut down our complexity. All right, so that was BigO notation. What wrap-up questions do you guys have before we get to lunch here? All right, so very conceptual. Again, I'll reiterate what I said from the start. don't worry too much about mastering this right now. We're not going to really use this too much in our curriculum. But again, these are popular interview questions. This is something that software developers are expected to know. So just speak the language. If someone says, hey, this is a constant time operation, that should register something in your mind like, all right, cool. That means that this doesn't, really impact by input size, etc. All right, cool. So let's wrap up our lecture there.